Hello and welcome to Kinetics 2. This is the second lesson in Big Idea 4. This podcast will focus on calculating the rate, and then we'll briefly introduce what a rate law is and how you can figure that out from the rate over time. So once we can calculate the rate, we'll look at how the rate of the reaction goes as it proceeds, and that will help us start to learn a little bit about what we mean by rate law. All of this is going to really focus on how we learned about in the last podcast. The molarity affects the rate of the reaction. So this is how much molarities of different things affect the rate. Okay, so we'll get started with how we can calculate the rate of the reaction. And this is going to be in your notes on the back of the first page. There's a sample calculation. That's the one that we're going to do. And then we're also going to get into the activity for calculating the rate of a reaction if you want to get both of those papers out. So you're ready. Okay, so the problem reads, basically we have this reaction. A decomposes into B and 3 C's. And the chemical A starts out as being 3 molar, and it's reduced to 1 molar in 180 seconds. What's the rate of the decomposition of A? And then we want to learn what is the rate of formation for B and C. So the rate of reactants is always going to be a rate of disappearance because they're obviously being lost. So disappearance. And this is going to generally disappearance. This is going to technically be a negative value, so this will give you a negative rate because you're losing it. The negative sign is not always written, though, because sometimes it'll just be defined as a rate of disappearance, and it's made positive. You just have to read the problem very carefully and ask and see if it's asking for a sign or if it's not asking for a sign. Over on this side, this would be the rate of appearance instead. So this is what's actually forming. So this will be a positive rate because you're forming at the rate of formation. All right, so since we're given the information for A, let's go ahead and calculate it for A. So for A, rate is equal to, so rate's obviously a change. Rate is the change in molarity over the change in time. And since these have deltas, what that means is it's going to be molarity final minus molarity initial. And these have to be for the same chemical. So if you're dealing with A, both values need to be for A. If you're dealing with B, both have to be B. And then the change in time would be T final minus T initial. T initial is often 0. It's just when the reaction starts. So just be careful because that value is often not given. So in this case, we're starting with a initial value of 3 and ending with 1. So it's going to be 1 minus 3. And it goes for 180 seconds. So that would mean that the T final will be 180. And this would be 0. So we end up with 2 divided by 180, which is equal to 0.011 molarity per second. And obviously this actually would have a negative sign because it's 1 minus 3. So this would be a negative. So you'd either put the negative sign or you would just list it as a rate of disappearance. You also could write the units like this. So it could be negative 0.011 molarity times seconds negative 1 because they mean the same thing. So these would be the disappearance rate for A. Well, what will we do then for B and C? Well, basically what we would be able to say is, okay, so for every 0. So these are kind of our new calculations, 0.011 molarity per second of, well, let's take the units out because that'll make it a little bit less. Okay. Take the units out just so we don't have so many letters going on here. Those units are still there. We're just not going to write them in the conversion. And this would be for A, right? So A. And you're basically going to do stoichiometry. So for every 1A, there's 1B. And that, again, that's going to come from up here. So it's a 1-to-1 molar ratio. So that means that B would appear at a rate of 0.11 molarity per second. And this would be positive because it's on the other side. You're going to have to figure out whether they're positive or negative based on their location. The calculations really aren't going to help you with this. It's got to kind of be logic. And then, all right, so then how, I got to make some space here for a second. We need to figure out also C. Now what changes here about C is that, let's see, just to delete. Okay, so if we want to do C, we have again the 0.011, that's for A, right? That's the molarity per second for A, times. Well, for every one A that you lose, you produce 3 C's. So it's going to appear 3 times faster than what A disappears. And again, this is coming from the mole ratio, the stoichiometric ratio that's in the balanced chemical equation. So this would be 0.33 molarity per second. And you could also write these in scientific notation. That obviously would be awesome as well. And that would be the value for C. And this is also positive because it's forming. So if we look at the activity that you were provided, let me clear the screen really quickly. Okay, so this is the first problem on the AP Chemistry kinetics activity. And so you're starting with reaction number 1 here. So we're going to do a few problems together just to kind of get things started. So reaction is the reaction, it's asking for the reaction rate between 0 and 2 seconds. So if we look here, between 0 and 2, so we're going to look over at the graph, we're given 2 molarity values. So we're going to take the equation, the change in molarity over the change in time, which is molarity final minus molarity initial over T final minus T initial. And so the molarity is going to be 1.4 minus 1.5 over 2 minus 0. Where the 0 went. Okay, so we're going to end up getting 0.1 divided by 2. So it's 0.05 molarity per second. And this will give you negative value because it's disappearance, right? All right, so this would be the value for the disappearance of N2O. The problem didn't ask for it, but you could find the appearance of either the N2 or the O2. This case, it's not asking for this, but this would be 0.05, right? Because it's a 2 to 2 molar ratio. And in this case, since it's 2 to 1, it would be 0.0. And these would be positive because they're forming 2.5 molar per second. All right, so now basically what you're going to do for the rest of this activity for part reaction 1 is you're going to look at how the concentration changes over time, because as we saw, the rate changes over time. So as the concentration changes over time, that could potentially affect the rate. So we're going to see if it affects the rate of the reaction over time. If the rate of the reaction is not changed, so this is where we get into something called rate law. So you may want to stop this video and actually work through your calculations and then come back and rewatch this. But all right, there we go. We had a cleared screen. What rate law means, so it's something called rate law. Okay, rate law deals with what we call order of reactions. And this basically is a really strange and kind of fancy way of asking this question. Does molarity of some chemical, in this case, we only have one chemical because it's a decomposition reaction. But let's say you have more than one reactant. Does the molarity of whatever reactant affect the rate? And if so, oops, I'm missing an I. If so, by how much? So If your concentration of your reactant decreases and there's no effect, no impact at all, the rate just stays the same no matter what. So rate is constant, no impact. That would be a constant. Rate is constant. This is known as a zero order reaction, or at least zero order with respect to that chemical. If your reaction, let's say, your molarity decreases, and as your molarity decreases, it decreases by the same factor, that would be known as, this is the same factor. For example, if your concentration is cut in half, molarity is cut in half, then your rate is also cut in half. This would be known as a first order reaction. Okay, so zero order means it has no impact. If I cut the molarity of the reactant, it doesn't matter. The rate still goes down by the exact same amount. If I cut the rate in half and the molarity in half and the rate also decreases by half, that's first order. Second order is if I cut my molarity by 2, but instead the rate is cut by 4. So basically it's doubly as important. This would be known as a second order reaction. And this would be basically continued. So you could have a third order reaction, so that if I cut my molarity by 2, my reaction rate would be decreased by a factor of 8 instead of 4. So it's exponential in its effect. So these are going to be the rate laws and the rate orders that we're going to deal with for the rest of the unit. That's our biggest part of kinetics, and we will study this in a number of ways. Today we just want to get a sense of how does the rate change over time. That's what this activity is focusing on. And then starting to see what these rate orders are. What would the data sets actually look like as a reaction ran? And that's what you'll be focusing in on this activity. Okay, thank you for listening.